Before proving the Schrödinger equation, we should know what is localized particle. So, localized particle. Localized particle is a quantum mechanical concept referring to a particle whose wave function is significantly confined to a small region of space. Now, consider a wave function psi x of a localized particle where potential energy is equals to 0. Now, the total energy of that particle, which is equals to kinetic energy plus potential energy, which is equals to kinetic energy, because we take potential energy as 0 and we take it 1. Now we'll prove how we get kinetic energy is equals to p square by twice m. So we know kinetic energy is equals to half m p square, and potential energy is equals to mass into velocity of that particle. Here the velocity is equals to momentum divided by the mass of the particle. Here kinetic energy is, we can write by putting the value of v. So you can get p square by twice m, which is in the equation 1. Now we know from the Broglie hypothesis the wavelength is equals to h by p, where h is the Planck constant and p is the momentum of that particle. Now we will divide both h and p by twice pi, and we will get twice pi into h cut divided by the momentum, which will take equation number 3. And we can write the momentum is equals to 2 pi by lambda into h cut is equals to h cut k, where k is equals to 2 pi by lambda. Now we can write k is equal to p by h cut, and we know h by twice pi is equals to h cut. From 1 we will take the total energy, which is equals to h cut square k square by twice m, and you can write E is equal to h nu. So I can write h by twice pi into twice pi into nu. So we can cancel out twice pi to twice pi. So cut square into k square by twice m is equals to h cut into omega, where omega is equals to twice pi nu, we all know. Which implies omega is equals to h cut k square by twice m, and we can take it as 4. Let us take the wave function psi x is equals to which is a plane wave equation. From equation 3, the function of position and time is equals to now taking common its cut can write p x minus e into t, which we take as 6, where omega is equals to e by its cut. Now differentiating the wave function or 6 with respect to time, we get curly psi of curly t is equals to here we will take a as constant. Which is the wave function and multiplied by minus I e by s cut, and I will take it as 7. Again differentiating the wave function with respect to position, we get curly psi curly x is equals to where we'll take a as a constant. And we can take it as the wave function multiplied by I squared into p. Again, differentiating the wave function with respect to position, or taking the second order derivative of that wave function, we get into p is equals to I by h cut to p into the wave function into I by square into p is equals to I by square whole square into p square into psi. It implies the second order derivative of the wave function is equals to minus p square by square square to psi, which will take it as 8, which implies which implies from 8 we can take e psi is equals to minus squared by iota into curly psi curly t, implies p square by twice m psi is equals to minus squared by I curly psi curly t, where the total energy we proved above is equals to p square by twice m. From 8 we get and this is the required time dependent Schrodinger wave equation, where 1 by iota is equals to minus I.